Good morning. This is the first segment of section 1.3. In this section, we are going to start defining the basic 6 trigonometric functions. There are typically in the trigonometry class, there's about 3 different ways to start this out. Some textbooks will use what's called a unit circle. Some will use what's called the right triangle approach. This textbook happens to use a point on array method or a coordinate method for establishing, which I personally think is actually a pretty good way to approach it. But it may not seem all of that intuitive at the beginning. But be that as it may, what we'll do is we'll establish a way of, in some sense, measuring a point on the terminal ray of an angle in standard position that then gives us the values of the 6 basic trig functions. And at the end, we will look at some exact values for some specific angles, because it turns out that it's really quite difficult to come up with, quote, a formula to express, say, the sine of, say, 23 degrees. That's almost impossible. I mean, certainly it is possible, but not something that we could really adequately approach in a class like this. It would get extraordinarily messy and computationally difficult. So anyways, without further ado, let's move over here and start discussing how we're going to define the 6 basic trig functions. Now, just a quick reminder, since these are functions, and we haven't really named them yet, but we will shortly, recognize that functions have both an input and an output, right? There's a domain and a range. And we will be able to talk more carefully about both of those properties. But just remember that the domain is the stuff that comes into a function, and the range is the stuff that comes out. And so far as we're going to do it currently, the stuff that's coming into these functions is an angle. It is a picture. It is a shape, if you will, in space. And what comes out of them are real numbers. So sometimes that subtlety is lost, because most students who haven't had any experience with trigonometry before, their only experience with functions is basically polynomials, where the input is a real number and the output's a real number. So the space from which the domain and the range elements come from is the same thing. And this is where we will start seeing a departure from that idea. So anyways, we'll probably have, my guess is we can probably do this in 3 segments, but it may run a little bit longer than that. So let's start with the definition of the 6 trig functions. And really this is trigonometric functions. So in order to define them, the first thing we're going to do is let's start, or let's say begin with angle POQ in standard position. Everybody remembers what standard position is, right? That's where the vertex is, the vertex of the angle is at the origin of the XY plane, and one of these rays is coincident with the positive x-axis. In almost every case, P is sort of the point that is not on the x-axis, potentially not on the x-axis. Furthermore, so we'll actually state that where ray OQ lies on the x-axis. should probably say the positive x-axis, but it should be understood from the term standard position. Now, we will also say let x and y be the coordinates of point P. So remember, if OQ is the initial ray, then OP is the terminal ray, and P is a point that's out there somewhere on that ray. Now, we're going to use this term, so let r, so lowercase r, be the distance from P to O. So this is from point P to the origin. Alternatively, we could say that that is the length of the line segment PO. Okay, so if you recall from college algebra, you did this thing where you used what was called the distance formula. And the way that the distance formula worked, and I'm just going to go ahead and write it here, recall that it was the distance between any 2 points is the difference in, let's say it's 0.1 and 0.2. So it's the difference in their x values squared plus the difference in their y values squared. And then you take the square root. Now, what you're seeing here is actually the Pythagorean theorem. Using a Cartesian coordinate system, but that's basically what it is that you've got a squared plus b squared square root equals c. And notice that d is always a positive number or it's non-zero. Now, in this particular application, what we've done is we've replaced d with r because it's kind of the radius of a circle that we will eventually get to. And one of these points, maybe say 0.1, is actually the origin. So it's 0 and 0. And the other position is point P, which has x and y. So this formula essentially, with a little bit of manipulation, reduces down to r is equal to the square root of x squared plus y squared. And note, P is not allowed to be equal to O. They have to be distinct points, and so this number is always greater than 0. So it's a positive number, strictly positive. Okay, so this is a bunch of words. Let's try to draw this in a picture that kind of makes sense. So let's say we have maybe an angle that's in quadrant 2. So here's our x-axis, y-axis. And now remember, since this is in standard position, there must be a point out here, point Q, right? And the terminal ray, since it's a quadrant 2 angle, is out here somewhere. And so there must be a point P. From the statement in the definition, it has a position of x comma y, and this distance from P to O, I guess I can put O here, is this lowercase r. Now, the other thing to note here is that assuming that we don't have, like a weird way of measuring it, let's say we have counterclockwise rotation, no windings, just somewhere between 0 and 360, this angle is, that's sort of the measure of that angle. Okay. So here's the 6 trig functions. What I'm going to do is I'm going to spell them out because sometimes that's a little confusing, and then I'm going to use the notation for them. So the first and most basic one is the sine function, the cosine function, the tangent function, and then we have the cotangent function. And I do them in kind of a different way than the book, but so be it. Then we have the secant function and the cosecant function. Okay, now the symbol that is used for these generally is lowercase letters. So you have, so these are the names of them, and the notation would be sin of theta. Now remember, this is a function, so it has to be a function of some variable, right? And the variable happens to be the angle. So this is what I was saying is the input. Sin by itself does not mean anything. And you may recall that kind of the similar sort of notation you had in college algebra was f of x, right? F didn't really mean anything, but f of x did have some meaning. Okay, so we have sine of theta, the lowercase sin of theta. And until you get really proficient at this, it is important to put this inside of a parentheses. You'll see that sometimes in the text where they don't, and it can get kind of confusing because there may be it may be something more complicated than theta. It could be like 2 theta plus 5 or who knows what. And without this parentheses, you're not sure if it is sine of 2 theta quantity plus 5, or if the angle is increased by a value of 5 or whatever. So just for the time being, and I will do this on everything that I do, is I will always write this in parentheses. And I hope you don't start off getting sloppy. So the next sort of symbol that's used for the cosine function is cos, and again, of theta. Now it could be of something else, but we're going to start out simple. Tangent is tan of theta. Cotangent is cot of theta. Secant is sec of theta. And cosecant is, csc of theta. Now, each one of these is defined in terms of one of these a combination of 2 of these parameters. So for sine, this is defined as y over r. So for whatever this point P is, there's an associated angle. And if you take y over r, you will get the value of sine for that angle. So sine of theta is defined as y over r. Cosine is x over r. Tangent is y over x. And then these other functions down here actually turn out to be the reciprocal of these. So we have the cotangent is the reciprocal of tangent. So that's going to be, instead of y over x, it's actually x over y. Secant is the reciprocal of cosine. So instead of x over r, it's actually r over x. And then finally, cosecant is the reciprocal of sine, which is sine is y over r. So cosecant will be r over y. So these are the definitions, and this is where we start from. Is we say that's why we did all this build up to this, standard position and all this other sort of stuff, is so that we could draw a point out there. Now, because we have this fundamental theorem of similar triangles, it does not matter if P is here or further out or back down here somewhere. It turns out these ratios will always be the same number for the same angle. And it's really based on sort of crudely, it's based on the slope of this ray, which we'll see an alternative way of kind of working with this here in just a minute. So, all right, first things, let me point out a couple of fundamental relationships. These are what are called fundamental identities. This is how these functions are related to each other. And so I'm going to point out first the really easy ones, which is that these functions are reciprocals of each other. They're basically the value flipped upside down. Now, there are situations in which one of these might be undefined, but provided that they're both defined, we've got some pretty simple relationships. So this is section 1.3, page 2. So this is your first introduction to these fundamental identities. So these are called the reciprocal identities. And here's how I'm going to actually prove one of them, and then I'm just going to write them all down because they're pretty basic. So note that sine of theta, which is equal to y over r, okay, is equal to 1 over the quantity r over y, which is equal to 1 over cosecant of theta. So forget all the stuff in the middle. Sine of theta is the reciprocal of cosecant of theta, provided that this is defined, because it is possible for cosecant to be undefined. And that's just because there is a, well, for a 90-degree angle, a 0 or 180-degree angle, y is actually 0. But be that as it may. So here's your first reciprocal identity. But note that that means that automatically cosecant is 1 over sine of theta. Again, provided that they are defined. Okay. Next, we have cosine of theta is equal to 1 over secant of theta. And similarly, secant of theta is equal to 1 over cosine of theta. Now, be very careful, because the argument, which is basically the thing inside the parentheses, has to be exactly the same. So this is not true that secant of theta is equal to 1 over cosine of x or some other kind of thing, or secant of 1 degree is equal to cosine of 7 degrees. It just doesn't work that way. The only way these identities work is if these are actually the same angle. But it's true for all angles, provided that these functions are both defined, which it turns out some of them are and some of them aren't. And finally, to kind of finish it out, tangent of theta is equal to 1 over cotangent of theta, and cotangent of theta is equal to 1 over tangent of theta. Okay, so you now have the 6 fundamental reciprocal identities, and you know, they're pretty easy to work with. What we're going to do is we kind of build up the skills to be able to use these at some point, but be that as it may. Okay, now there's also what are called the quotient identities, and this quotient is a fancy word for ratio or a fraction. So note that let's look at the ratio of sine of x to cosine of x. Now, I'm sorry, I don't want to shift into x's. Let me stay with sine of theta, cosine of theta. Okay, so note, sine of theta, again, is y over r, and cosine of theta is x over r. Well, notice, algebraically, this reduces to just y over x, which happens to be equal to tangent of theta. Now, if we do sort of a similar thing where we take the ratio of secant of theta over cosecant of theta, now again, note, secant is r over x, and cosecant is r over y. Now, when you algebraically reduce this, it becomes y over x again, which happens to be equal to tangent of theta. So for tangent of theta, there are actually 2 different quotient identities, and these 2 things happen to be equal to each other as well. So to kind of summarize that, I'm going to write this in one long chain of equal signs. So tangent of theta is equal to sine of theta over cosine of theta, which is equal to secant of theta over cosecant of theta. Now, just so you're aware, and I've seen this happen a bunch of times, so I'm going to just try to point this out. Sine does not equal secant, cosine does not equal cosecant. In fact, there is no place where that's true. There's no angle for which cosine is ever going to be equal to cosecant, and there's no angle for which sine is ever going to be equal to secant. It's just it's the ratio happens to be equal. And again, both of these have to be defined. Now, there's a similar relationship for cotangent. And since cotangent is the reciprocal of tangent, basically all of these equal signs get flipped upside down. So cotangent is equal to cosine of theta over sine of theta, which happens to also be equal to the ratio of cosecant of theta to secant of theta. And those are the fundamental, the quotient, another class of fundamental identities called the quotient identities. And we use these collection of 6 equations and another 6 equations all the time, especially when we start getting into chapter 5. But we'll use it pretty. We'll use it extensively in the next. In some of these sort of I wouldn't call them application problems, but where we try to show that how these functions are all somewhat interrelated. Okay, so I think this is a good stopping point. I think this particular video might be a little bit short, but that's fine. I will see you in the next video where we will actually use this to solve some problems where we actually find the trigonometric the trigonometric function values for specific angles. Okay, see.